So welcome students, and in this video we are going to talk about something called a fundamental matrix. Okay, and by the name of it you do realize it is a very important concept. So what is it? So essentially let us consider this system. So consider the system, so a variable coefficient system, n cross n system, which is given by x prime equals to at times x. Yes, where a of t, this is a variable coefficient, of course, is a continuous n cross n matrix function. Okay, continuous n cross n matrix function. Clear? Let me put it this way. So basically what I mean is, if all the coefficients of a and they are going to be continuous on whatever interval we are going to define this system. Yes, now the thing is this, see, we know that if we choose, see, if one choose f of ty to be 80 times y, sorry, f of tx to be 80 times x, tx to be 80 times x. Yes, and since a is given to be continuous, see, here with respect to t, a is continuous, right? Because a only depends on t, and f of tx with respect to just the second variable x, it is c1, right? So basically we can use the Picard's theorem, which we talked about in the earlier video. So if we choose this, then by Picard's existence and uniqueness, Picard's existence and uniqueness one can find a unique solution, right? One can find an unique solution. And what is the solution? Given by, let's just call it x of t. Okay, and the solution is in, of course, is in c1 of I. Yeah, c1 of I to Rn, satisfying what? That some initial data, right? Satisfying x at the point, let's say 0 is x naught. Okay, so whenever you are given this initial data, you have a solution which passes through that initial data, that is via Picard's existence and uniqueness. Clear? Now what happens is this, see, if for this system, let's just call this system 1. Okay, now see, this x naught is in Rn, right? Yes, and you see that now if one choose x naught, okay, the vector x naught, okay, to be, let's say, ei. What is ei? Which is nothing but the unit vector. Okay, so 0 0 and 1 in the ith variable, and then 0 0 0 0. Yeah, let's say this is a element in Rn. So basically this is the ith entry, the ith unit vector. If you choose that, then look at this system. See, consider this system now. So consider the following system. See, what is the system? It is given by f prime equals to 80 times x, right? 80 times x, and x at the point 0 is ei. Okay, given this system, let's just call this system as 2. Okay, 2 and I, let's just call it 2i. Yeah, because this depends on I, right? Then there exists, we know that a unique solution x, let's just call this solution as xi of t, which is, of course, is in c1 of I to Rn, right? Satisfying 2i, this equation for what I? For I between 1 and n. So what I am trying to say is this, see, the thing is this x naught. So basically what we are saying is this equation 1, okay, that is the trajectory which a particle is following. Yes, that's what given. And what is x0 at the point x naught? That is basically saying that at the point t equals to 0, so when time is 0, it has to pass through the vector x naught, right? So we can choose the vector to be e1, e2, en, right? So ei's are the unit vector. We can choose that, and for each such choice I will get a xi, right? I will get a xi. Now the thing is this, you see, let us define this. Let us define this phi of t. Let's define this phi of t. What is phi of t? Phi of t, this is what we are going to call a fundamental matrix, which is nothing but x1 of t. So if you understand x1 of t is basically a vector in Rn, right? So you just write down as a first column. So what is the first column of phi? Which is x1 of t. What is the second column of t? It is x2 of t. Okay, so what we are going to do is we are going to define this new matrix. You understand what is the definition? That the ith column of the fundamental. So basically the ith column of phi t. Phi t is what? We will call it a fundamental matrix. Okay, fundamental matrix will be the xi's. Is it okay? So basically the xi of t will actually form the ith column. Is it okay? So that is your phi. Now you do realize that phi is a n cross n matrix, right? And since x1, x2, xn, they are all c1, so basically phi is also c1. So you do not really have to worry about it. Yes? Now, okay, fine. Now the thing is, there are some few properties which we really need to understand. Properties. First of all, if you look at it, you see phi, where is it defined? Phi is defined on I. You see, for every t from the interval I, you are going to get a matrix, n cross n matrix, right? So phi as a map, yeah, it is mapped from I to where? It's a matrix to n cross n, okay, over R. So that is your phi is C1, okay. It is C1. So at least continuously differentiable. Why it is C1? Because you do realize that every component of it is continuously differentiable. So basically phi is continuously differentiable. Is it okay? Right. Now the thing is, this is the first property which we know. Now the second property, this property I am going to write it down. You have to verify it. It is very easy. Yes, it's actually trivial. So you please verify it. You see phi, since it is C1, what happens to phi prime of t? You can actually show that phi prime of t is nothing but AT times phi of t. Is it okay? Yeah, this is what phi does. Yes, and if you check this part, you see also, do you realize what phi of 0 is, right? Phi of 0 is nothing but, you see, x1 at the point 0, you see, this is x1, the vector x1 at the point 0, x2 at the point 0, right, and xn at the point 0, right? That's your phi of 0. So what is that vector? What is phi 1 at the point 0? You see, phi 1 at the point 0 is nothing but e1, right? So the first vector, so it is 1 0 0 0, and the second one is 0 1 0 0. You understand? So the last one is all 0 zeros, everything is 0, and it is 1. So basically it is nothing but the identity matrix. Is it okay? So phi, hence let me put it this way, hence phi satisfies the matrix phi, okay, that satisfies the matrix differential equation. Okay, so this is a different kind of differential equation. It's called a matrix differential equation. And what is it given by? Given by phi prime of t equals to AT times phi t, right? And phi at the point 0 is identity. Yes. Now I really do not have to tell you that since phi at the point 0 is identity, you can use Abel's theorem, right? Yes, you can use Abel's theorem, and you can say that the determinant of phi of t is never going to be 0 for all t in I. Yes, see, the thing is, initially what is happening is this phi at the point 0 is x1 at the point 0, x2 at the point 0, xn at the point 0, right? See, x1 at the point 0, x2 at the point 0, which is nothing but the identity matrix. So phi at the point 0 is identity matrix. Is it okay? Now what happens is, of course, you in the last video we talked about this Abel's formula, right? What is Abel's formula? It says that the Wronskian of x is nothing but Wronskian at some point 0 times the exponential of at, right? Trace of at. Now the thing is this, see here what is happening is, you take that arbitrary point x0 to be 0 here. So if you take that, then you do realize that since that matrix, if you taking the Wronskian, that Wronskian of the identity matrix is 1, so it is basically never going to be 0. Okay, so in that case, determinant of phi of t is non-zero, which means therefore phi is non-singular. Is it okay? So it is basically a non-singular matrix. Okay. What are we using here? We are using Abel's formula. formula. Okay, so you guys have to check this part out. Please do that. Yes. Okay, so now let's look at some examples. Okay, what are the fundamental matrices? So let's look at the examples. See, the thing is, you can easily check that if you define phi of t0, let's define phi of t0, which is given by e to the power at. If you define this thing, yes, you can see that this is the fundamental matrix, or let me call it principal fundamental matrix. I will explain to you what is principal, why we are calling it principal fundamental matrix. Again, this matrix also we will call it a principal fundamental matrix. Okay, principal. I will explain to you why we call it principal fundamental matrix. Matrix of what? Of the system. I think you can guess this part. It is given by x prime equals to the constant coefficient system, x prime equals to a times x. Is it okay? A is constant. Okay, of course, n cross n matrix, A is a constant. So you can check this part. Yeah, so if you are defining phi to be this, then phi will be a principal fundamental matrix of this system. Okay, and you do realize that any solution of this system in that case will look like phi of t0 times x naught, right? So that's just any solution which will look like this. Okay, so now one thing I want to, yes, principal fundamental matrix. What is the principal fundamental? You do realize that, you see here, this x1, x2, x0 equals to EIs we chose, right? EIs are what? EIs are basically the basis of Rn. Is it okay? Now the thing is this, if we change the basis of Rn from EI to some other basis, right? So you choose any n linearly independent vectors and you have another basis. So let's say, you know, A1, A2 is another basis of Rn, right? It can have another many different bases, right? Let's say this is a basis of Rn. Okay, now if you take this equation, x prime equals to at times x, and x at the point 0 is ai, let's say, yeah, you will get a different set of xi's, different set of solutions, right? Those solutions also you can put it like this, like phi. Yeah, you can define a different phi, and that will also give you a fundamental matrix. Again, the same sort of thing, same properties hold. All the same property holds. Of course, phi of 0 will be something else, but the thing is, doesn't really matter. Exactly the same, exact same. So phi will divide phi prime t equals to 80 times phi, and all other properties will be same, except that phi of 0 will be a little bit different. It will be a different matrix, which is, by the way, non-singular. Is it okay? And again, by Abel's formula, you can prove that it is a non-singular matrix. So that's not a point. Huh? The thing is this, you see, there can be many different fundamental matrices for a given system. You understand? Based on the basis which you are choosing. Generally speaking, if you are choosing the standard basis, which is EIs, what I chose here, then that fundamental matrix, we will call it a principal fundamental matrix. I hope this is clear. Okay, right. So this is the thing. Now the thing is, you can also find, I mean, if you want, yes, so let me call this thing as A and let me write down B. What I want you to do is, please check, try to find out the fundamental matrix for the, so find out the fundamental matrix, of A, the system, of the system x prime equals to 0, 1, minus 1, 0 times x. Is it okay? Try to find it out. See what, if you can do that part. Yeah, please do that. Okay, so that is it. Right. Now the thing is this, we are going to prove a very important theorem now. The theorem says is this. So what is the relation between these fundamental matrices? Okay, so theorem. So it says that if phi of t is a, I am writing it like this, a fundamental matrix Fm, okay, of the system x prime equals to 80 times x. Okay, so if you have a homogeneous system and phi of t is given to be the fundamental matrix of this homogeneous system, okay, then any constant non-singular n cross n matrix matrix, then for any constant non-singular matrix, n cross n matrix, okay, C, phi t times C is also a fundamental matrix, of the same system. Okay, so let's say what I am saying is this: if you have one fundamental matrix, you can of course produce another one just by multiplying with a constant, and please don't change the order. So it is phi t times C, yeah, a t times x of the same system. Clear? Also we can say that every, okay, fundamental matrix of the system x prime equals to a t times x, okay, of this system is of the form, so basically you can't find any other form of fundamental matrix except this, of the form phi t times C. Is it okay? Where C is as above. So basically a non-singular n cross n matrix, okay, constant matrix of course. Okay, so what is the theorem? It's very simple. So essentially what I told you is this: you see, there is a principal fundamental matrix and there are other fundamental matrix depending on the basis which you choose, right? Yeah, so given a system, you can have like infinitely many fundamental matrices depending on what basis you are choosing. What is the principal fundamental matrix? It is nothing but the matrix which you get with respect to, so basically the solution which you are going to get with if you are choosing the unit standard unit basis elements. Okay, so E1, E2, En. Now the thing is this: what this theorem says, that what about the other fundamental matrix? Is there any relation between any two fundamental matrices? What it is saying is this: it doesn't really matter what you are going to choose your basis. The fundamental matrix essentially will look like, if one is given to be phi, another one will look like phi t times a constant C. Yeah, and it's also true that every fundamental matrix will look like this. So you can't go on showing something else is a fundamental matrix. Okay, right? So let's see. Okay, so first of all, let's say if phi t is a fundamental matrix, we have to show that phi t times C is also a fundamental matrix. It's very easy. Okay, now since phi t is a fundamental matrix, what did I tell you? This is true, right? Phi prime of t equals to a t times phi of t. Now this is quite easy to check, as I told you, of course. Yes, please do that. So this is one. Let's just call that one. Okay, now you see, I have to show phi t times C is also a fundamental matrix. So let's look now. You see, phi t times C. Let's just look at the derivative of this. What is it? Constant C is a constant matrix, right? So the derivative of that is basically nothing. So it is essentially phi prime of t acting at C, right? Again, phi prime of t, we know it is a t times phi t, right? Phi t acting at C. Yes. So you see, by matrix we know that associativity property holds, right? So you can write it as a t times phi t times C. Okay, now phi t times C, phi t times C prime is nothing but a t times phi t times C. Yes, therefore phi t and phi t times C are both solutions. Okay, therefore phi of t and phi t times C are both solutions. Of the matrix of this equation. You see the matrix value differential equation. Okay, so phi prime equals to a t times phi. Okay, satisfies this. So this is the matrix differential equation. Please remember, yes, the fundamental matrices, they satisfy the matrix differential equation. Okay, right? Okay, so now you see, the thing is, you have to also show that, since the important thing is how do you check something is a fundamental matrix. First of all, you check it sort of satisfy the matrix differential equation, and the next check is what is about the determinant, if it is non-singular or not. And you see, since determinant of phi of t, this is non-zero, right? Because phi of t is given to be fundamental matrix, and therefore determinant of phi t times C is nothing but determinant of phi t times determinant of C, and since determinant of C is non-zero because C is given to be non-singular, you see, non-singular constant matrix. Okay, so this is also going to be non-zero. So it's trivial, right? So you can actually see that phi t times C is also a fundamental matrix. Clear? Very simple. Now we have to show the converse part. So what is the converse? So let's say phi of t, any two fundamental matrices is given to you. Yes, we have to show that one is a constant multiple of another. So basically, phi1 and phi2 are two fundamental matrices. You have to show that phi2 is nothing but phi1 times c. Yes. Okay. So conversely, let's do that. Conversely, we have to show that let phi1 of t and phi2 of t and phi2 of t be two fundamental matrices, matrix solution, okay, of the system x prime equals to at times x. Okay, now the thing is this, see, if this is the case, yeah, just look at this thing. Phi and phi inverse both are non-singular, right? So I can talk about the inverses. Yeah. So define this new matrix C of t, which is nothing but phi2 inverse of t times phi1 of t. Let's just call that. Okay. Now if you do that, see what is phi1 of t in this case. Phi1 of t is nothing but phi2 of t times ct. Is it okay? Yes. And if you take the, you see, phi1 and phi2, let's say C, phi1 and phi2 are both C1 matrix functions, right? So C is also C1, right? So we can take the derivative here. Now differentiating what we have, differentiating one has differentiating this part. Okay, I have phi1 prime of t, right? Phi1 prime of t is nothing but phi2 prime of t times ct plus phi2 of t c prime of t, right? Now you see what is phi1 prime of t. Phi1 prime of t is nothing but a of t times phi1 of t. Yes, and what is phi2 prime of t? It is a of t times phi2 of t times ct, yeah, plus phi2 of t times c prime of t. Yes. Now you see phi1 is phi2 times ct. Phi1 is phi2 times ct. This is phi2 times ct. So basically this part and this part we can just cancel it out. So basically you can take the one matrix to be on the other side, and that will actually give you 0. Now essentially what you have is this phi2 of t c prime of t is nothing but the 0 matrix. Yes. Phi2 is what? Phi2 is a fundamental matrix, so that's a non-singular matrix. If you take phi2 inverse on the both sides, essentially that will give you C2 t is 0, which basically says that Ct is constant. Is it okay? So if Ct is constant, you do realize that phi1 will be phi2 times a constant matrix C. Okay? So with this, I am going to end this video.